In today's video, we're going to talk about confidence intervals, and those are going to be interval estimates for a population mean. We'll use the ideas of confidence intervals in the rest of the class for chapters 10, 11, 12, 13, and 14. So there are definitely items that we need to know what we're finding and how to find them. So let's start. Let's think about what we just worked with in the last chapter. And in the last chapter, we dealt with having populations who were a specific population size, capital N we'll say, and we're measuring some variable on this chapter's context. So there's some type of a measurement. You might be measuring the length of someone's index finger, or you might be giving someone a test, you might be weighing someone, you might be measuring someone's height. So the context is you are getting numerical data. And this population has parameters. And the parameters that we would have is all these capital N items in here. There is a true mean of all these specific individual items. And then we have a true standard deviation for these. Now these things really, in general, are going to be unknown. Usually we don't know a parameter because we would have to do a census in order to get every single value. So for this unit, we're going to have kind of a little, we're going to kind of like push the limit a little bit. We're going to assume that this is known, that we know what the variability is, but basically we're going to say we don't know this idea. We don't know what the mean is. That's going to be unknown. And so if we are trying to figure out what the mean is, the population mean, this parameter, what would we do? We would take a sample. And when we take that sample, that would result in an X bar. And we would have used a specific sample size, some specific sample size. And we know the larger this sample size is, then probably the better estimate we think this X bar will approximate the actual population mean. But we really would like this number to be exactly the same thing as this number. It's just very, very unlikely that that's going to happen. So what do? We actually calculate an X bar. This guy is a statistic. Remember, there is a difference between having a statistic and a parameter. A parameter is an exact value that is from the population, and a statistic is collected from sample data. And so what we do is we calculate something called a confidence interval. A confidence interval for a population mean. We don't know this guy. We would love to know him, and if we knew what he was, we actually wouldn't worry about taking samples to estimate him because we'd know him. But we take samples of a specific sample size, again, the larger the better, and we use this statistic to help us estimate what this value is. Now this is a point estimate of what the population mean is. A confidence interval will basically be an interval estimate. And how do we calculate it? We take the number we got, the X bar, plus or minus some specific Z star value, and I'll talk about that in a minute. That will depend on what level of confidence we want in our estimate. And then we take this population standard deviation for individuals over the square root of n. And remember the context of this, the standard deviation over the square root of n, that was the standard deviation for sampling distribution of X bars. If we continue to take samples of size n from this population, have X bar 1, X bar 2, X bar 3, etc., remember these X bars that would result would end up centering at this value, and also the standard deviation for the X bars would be this calculation right here. But we're only going to take one sample. We're not going to take a whole bunch of samples of size n. We're just going to take one. And so let's look down at our example, and we'll go back and see how do we actually calculate this. It's really quite easy, but we have to remember what we actually calculated. So let's look at the example. So I have an example that, again, this data comes from your textbook. And some third grade students were given at some suburban school district, were given some type of a reading test. We have 44 third graders, and here are the resulting scores. It's not important to know how high what the high was and what the low was as far as what type of scores you could get. Possibly this is out of 500 points. We surely would hope not, but that's not important to know what the high score is that someone could score on this exam. Here are the results of 44 third grade students. So I made a little graph. I wanted to see what type of a distribution do I have. I would like in this chapter to have normal distributions. Okay, so we know that the central limit theorem allows us to have smaller sample sizes, and we can have sampling distributions be approximately normal as long as we have our sample size relatively big. But the first thing I want to do is I want to graph this data, which I did, and I find from my histogram that it looks pretty normal. And it looks like it's skewed a little bit off to the left this direction, but it doesn't look too bad with only 44 numbers. I also found the mean and the standard deviation of my distribution. Now, on part B, I have supposed that the standard deviation of the population is really known to be 11. So I'm talking about this guy. We're going to say that we know that we have this big population of third graders in this school district, and we know that the standard deviation is 11. We just don't know what the mean score would be for that specific school district for this reading test for third graders. So now we're going to calculate something called a 99% confidence interval for the mean score for the school district. And the basic is we're trying to get an interval estimate for what this value is. We already know a point estimate. Our sample of 44 yielded 35.09. We really don't think that this sample, this x bar, is exactly this value. We know that when you take more samples of size 44, you're going to get variability, and it's very, very unlikely that I happen to get a sample that is dead on exactly the same as this population mean. So, our calculation, here's our formula. Now, the context of having a 99% confidence interval, you should think, well, where'd you get that z-value from? So first of all, a 99% confidence interval is getting a z-value that finds the area symmetrically if I have 99% of the area underneath the standard normal distribution between those values. So whatever this z-value is, we know that this z-value is just going to be the opposite. And so we could go through and say, all right, that's 99%, so we're missing 1%, which would have to be split among the tails. Oops, my lead broke. And so that area there would have to be 0.005, and that area there would have to be 0.005. And then we could go through and grab our book, and we could look up in the back of the book, the front of the book. We could go through, and I don't know that this will focus real well, but looks like it does. I could look up here and try to find 0.005. And I would find 0.005 is kind of right in between this value and this value. And that would correspond with negative 2.575. So this lower value would be negative 2.575, and this one would be positive 2.575. Okay? And then we can use that value to complete our confidence interval, and I have the calculations here. So if I'm finding a 99% confidence interval, I need to think of the symmetrical standard normal curve with having 99% between two numbers and find those z-scores. And you see I have a plus and a minus. I have two of them right here. And I take what I got plus or minus my z-score that is determined by the level of confidence that I'm going to have times the individual standard deviation over the square root of n. And remember, this is really finding me what the standard deviation is of the sampling distribution of x bars. And I get this interval. So I can think, I'm quite confident that this mean that I'm looking for, that I don't know, this number right here that I don't know, I'm quite confident that it's somewhere between these two numbers. Why? And here's the definition of what a confidence interval is. 99% of the time, here's this confidence interval, basically about 31 to about 39. When I calculate a confidence interval, this is the context of the meaning. That means 99% of the time, a calculated interval like this one will contain the actual population mean. This number that I'm looking for, this little mu that I'm looking for here. So we have a 99% chance that our interval actually has the population mean in it. Now, what does that mean? It means if I went to this population and I took a sample size of 44 and I got an X bar, and then I did plus or minus the 2.575 times the standard deviation over the square root of n, and I calculate this interval. I found the low number and the high number. And then I do that again. I calculate, get 44 more numbers. Now this X bar is going to be different than this one. It's very unlikely that they're going to be the same. And I know my hand's in the way when I write. I'll try to move it a little bit. But I do this over and over again. I keep taking another sample of 44, and I get another X bar. And again, diddle these down, and I get another interval. All of these intervals are going to be different because this X bar is going to change each time as I collect more data. Now I do this, let's say, 100 times. I'll write this last one down. Oops, that's a 5, 7, 5. You get the idea. I'm not going to erase it. Now, theoretically, this is a 99. Each of these is a 99% confidence interval. Theoretically, 99 of these will actually have this true population mean somewhere within these intervals, and one of them will not, because it's a 99% confidence interval. So the confidence level tells us what percent of the time a calculated interval will contain the actual population parameter. So it's an interval estimate between two numbers, and we're going to have a certain level of confidence that our actual population mean that we don't know is somewhere within that interval. However, we know that it's not 100% accurate. In this case, only 99% of the time will this interval actually have the population mean somewhere within these values. Now we can very easily change to a different confidence level. Let's turn the page. Let's look at E first, and then we'll go back and look at D. And I said find a 95% confidence interval for the mean score. So now we are not going to be as confident. So we know we took one sample. We got 35.09 for the mean. And if I want a 95% confidence interval, I want to use a z-value that is going to have this area between the numbers be 0.95, which we know these numbers are very close to 2 and negative 2. However, this area down here of 0.025, this of 0.025, now these all add up to a density curve of 1. This value would be a z-value really of negative 1.96, and this one of positive 1.96. So we have what we got, plus or minus the z-value according to what level of confidence we want, times the standard deviation over the square root of n, this being the standard deviation of the sampling distribution of X bars. And notice that my interval is not as wide as the previous page. This is has less distance between these two endpoints, but I don't have as much confidence. 95% of the time when you do this calculation with a sample, the interval that you get will have the actual population mean somewhere in here. That means, again, if I think of doing this 100 times, take another sample of 44, find the mean, crank out the interval, get another sample of 44, find the mean, crank out the interval using a 95% z-value. If I do this 100 times, theoretically, 95 of these intervals will have the actual population parameters somewhere in there, but 5% of mine, or 5 of mine out of 100, would not have the population. And I really have no way of knowing whether this one is one of the 95% that actually has it lying within, or it's one of those bad ones that doesn't capture the population mean. So we always have a chance that we might think it's in here, but we have a chance that it's actually not in there. Now, go back up to D. Would you trust your conclusion from B, or even from this one, to be a confidence interval that is trying to, again, calculate what the population mean is for the whole school, if you knew that all the students came from a single class? And so if those 44 kids that were from this, the calculated number that I got here of that mean score for that X bar score for those 44 kids, if that was all from one classroom, this would not be a representation that would help me know what the entire school district was doing, because we don't know that one class would be representative of all. It's kind of like if we took our statistics class and I asked you questions about some topic, and then I inferred that that's what everybody in our school would think. You guys as a group could be different from the other people in the school just because you love to take advanced math. Now, the last topic that we want to look at in this section is what is margin of error and how large of a sample size do I need to get a particular margin of error. So let's just look down at the example, and then we'll look at what it is to find a margin of error. So I have how large of a sample size would we need on the average in order to have our margin of error within 2 points with 95% confidence. Well, here's a confidence interval. This component is the margin of error. A lot of times I'll just call it capital ME. So it's not me, it's margin of error. This is what we're talking about. We want to know how large of a sample size would we need to have the margin of error be within 2 points with 95% confidence, which means I want to produce a confidence interval with a particular sample size that's going to end up being X bar, which I would get from my numbers. I don't know how many yet. Maybe it's 44, maybe it's 50, maybe it's 70, whatever the case is. And we want the calculation of the z star times standard deviation over the square root of n to be only 2. So how do we calculate that? Well, we know that we want, again, the z star times the standard deviation over the square root of n to be 2. You really don't need to worry about on my notes that you'll see shortly. You'll see that I have a less than or equal to sign there. Don't worry about the symbol of the inequality when you actually do the calculations. You can do it with equality and then go back and substitute what we need to. All right, so I plugged my numbers in. And I have 1.96. Oh, I guess I changed that to an equal. 1.96 is what the z value is for 95% confidence. This is the standard deviation that we're assuming to be true. We have here, we don't know this sample size, so that's where our square root of n is. So we have z star value over the standard deviation over the square root of n, and we want that margin of error to equal 2. So now all I need to do is solve for the square root of n, or for n in general in the end. So I multiplied both sides by square root of square root of n, and divided by 2. So multiplied by square root of n, multiplied by square root of n, that cancels here. And then I also divided by 2, and that results in this. This calculation comes out to be 10.78. And then I need to square both sides. Now, the thing you need to remember is whatever you get here, you need to round up to the next integer. We can't have a sample size that is 116.2. And if we actually use 116 and round that off to like the nearest integer, 116 will really give us a margin of error that is just a tiny bit bigger than 2. And if we don't want it to be any higher than 2, we need to go round up to the next integer. So 117 is the first sample size that will cause that margin of error to be 2 or less. Okay, so we have to sample quite a few more numbers, because notice up here on part E, our margin of error with a sample size of 44 with 95% confidence was a 3.25, and we're trying to make that margin of error go down to 2. And 117 will do it. Now, very last thing is we do have to have some cautions, and you can read more about this in your textbook as well. But we are working with simple random samples. We don't want to have a biased type of selection. There are other sampling techniques that are possible. So the formulas that we're working with are dealing with using a simple random sample. You don't want bias. If you collect samples, we know that outliers are going to cause us issues. So if we looked at our sample of numbers and we had an extremely low number or extremely high number, that's definitely going to affect our X bar, which is going to cause us to have a confidence interval that won't be very representative. Now, if n is small and the population is not normal, our confidence interval, once again, is not going to be real accurate. We do want larger the larger the sample size, the better. The more accurately we can get a confidence interval and feel, quote, confident in it. But we'll find that when your sample size is at least 15, that these confidence intervals are actually quite accurate, even if you had a population that was non-normal. Now, the catch on this is, as we talked about before, you have to know what the standard deviation is of the population, which is kind of hokey. And if I go back to this little picture, remember, this is the population that we really want this number. We're going to say we don't know it. Why in the world would we ever say we know this? Well, we'll get into that in Chapter 11. Right now, we're just going to say, all right, we're going to assume we know what the variability is from past experience. All right, so now you're ready to do some practice questions.